we will discuss maybe 2 or 3 of them, and the first of them is the powers of matrices. So that's my first slide. How to compute matrix powers via diagonalization. So it's a relatively simple slide actually, because everything we have done already before, everything we need we've done already before. So imagine I have a matrix, square matrix as before, of size n times n, and imagine for such a matrix we have established diagonalization result. I showed you how to do it at least 3 times on 2 days ago. So diagonalization, as we discussed with you 2 days ago, it's the ability to present 2 other matrices, which we normally call P and D, or actually your yellow book sometimes use the letter M for P rather than P, but I like P more than M. So these 2 matrices, they must be of the following qualities. First, P must be invertible. Secondly, D must be diagonal matrix with some entries on the diagonal, and the rest of them should be 0. It's the second quality which must be present for this pair P and D. And the last quality which is present is this quality, is this identity should be true. Your A matrix must be representable as a product of these 3 factors. I mean, if you smart enough and your guessing machine is so powerful that by looking at the matrix you can come up with such pair of matrices straight from the top of your head, that's all you need to do to find a diagonalization. For the rest of us, for the mere mortals, the rest of us who doesn't have this powerful guessing machine, we have this eigenvalue and eigenvector analysis we have developed for 2 weeks now, almost 2 weeks now, which helps to find this mysterious pair of matrices P and D. Okay, so having these 2, if you have this diagonalization, then computing the powers of matrices becomes a lot easier. And why we need the powers of matrices, I will give you one example today. There will be more examples in the yellow book. So first, let's just try to compute the power a to the power k. K will be integer, positive integer. So basically, for such powers, you just multiply a with itself k times. When k is not so large, you basically can do it directly by multiplying a out. When k is a large number, or as a matter of fact, if k is any number and you're looking for a formula for this part of the matrix, that's where the diagonalization will be helpful. Because look what you can do. You can just simply do this. You can take this representation for A matrix and you can use it k times across this writing. So here it is. I replace my first A with the PDP inverse factors. I replace my second A with the PDP inverse factors. I replace all of them like so. As here's the last one. Here's the last replacement. All I have to do now, I have to just put the brackets in a different order. I have to use the associative law of matrix multiplication. If I use that law, then I can rearrange the factors like this. These first 2 PG, I'll just copy them. But then this P inverse, I will couple with this P, like this. And the next P inverse, I will couple with the next P. Of course, I will put D in between. D is still here, but the next P inverse I will couple with the next P, and I can do it all the time for this inner, all of these inner P's and P inverse. I can do this coupling, like the last coupling will be here, P inverse P, and then the last 2 factors, P and P, D and P inverse, they just copied as they are. I have done nothing but just simply change the position of brackets here to emphasize different order of multiplication. That's the associative law of matrix multiplication. Each bracket here can be now shortened to the just identity. That's what the inverses are for, to cancel the matrices. So each bracket becomes just the identity, PD, identity, D, identity, many other D and identities, like this. Well, clearly, identities, they don't change anything. We can drop them from the presentation. How many Ds will stay here? There will be 1 D for each original bracket here. Altogether, we had K brackets, so altogether we will have K Ds. Which is the power, K power of D matrix, and we come down to the expression like this. P inverse, D power K, P, D power K, P inverse. even though you see what happened, we reduced the computation of the power of the matrix K to the computation of the power of the matrix D. So either way, you have to compute the power, but the advantage here is that for the diagonal matrix, and that is something we discussed with you 2 days ago, for the diagonal matrix, computing the power, it's no longer a big problem, because for the diagonal matrix, the arithmetic goes in entry-wise. So the kth power of D is simply the diagonal matrix where you take each entry to the kth power. Each number on the diagonal, you just take to the kth power, and that's all you do. See what happened? Rather than multiplying k times with itself via complex matrix multiplication rule or algorithm, you do just very simple arithmetic with the diagonal entries, and then you basically do only 2 matrix multiplications, one of them between P and dk, and the other one between the result of this multiplication and P inverse. K sequential multiplications, we just replace them with 2 matrix multiplications. That's a significant advantage. No matter how large K is, you can always do this. And you hardly can do this. Even if you have powerful computers, sometimes you can't do this. And that's the very significant advantage of having matrix diagonalized. Trust me, it's a very significant advantage for the applications. Computation-wise, I mean, 80% of the jobs your computers do, they won't be able to do that unless they have this diagonalization method. Matrix multiplication is heavily involved in many computations in the modern computers, actually, and in particular powers of matrices. Now, you can do similar analysis with the inverse, actually. So what I claim actually is that the inverse of a matrix, which is given in a diagonalized form, the inverse of such matrix can be computed by just inverting the diagonal part here and keeping P and P inverse as it is. I will convince you that this is a good formula for the inverse. And that's again a great advantage, because if you have your matrix diagonalized and you're looking for the inverse of that matrix, finding the inverse is not an easy process. It's a row echelon form method in general, of course. But here, if you have your matrix diagonalized, all you have to invert is the D matrix, diagonal matrix. And for the diagonal, again, finding the inverse, it's a simple task. You just invert every entry. So let me convince you that actually the inverse of A can be computed like so. If I want to convince you that, I have to just check that with such choice for the inverse, if I multiply A with the A inverse, I will come up with the identity. Okay, let's do that. What I will do, I will just use the, again, diagonalization result for A matrix and the suggested result for the inverse. Here it is. And I will multiply everything out. Again, I will change the order of brackets. Look at this. I will change the order of brackets. Here we go. PG, these first 2 factors I just copy. Then I combine together P inverse and P in the middle. And G inverse, P inverse, I copy again, like this. This in a block, it's the identity matrix, like this. Identity can be dropped from the matrix multiplication. And we have another inner block, D and G inverse, which again, another identity matrix, like this. Again, you can drop the second identity. And the P and P inverse together, which are left, they also go into the identity matrix. And that's my argument why such a choice of a matrix, will play the role of the inverse for the matrix A. Well, strictly speaking, you have to check in the other order as well. You have to multiply A inverse with A and do the similar manipulations. I'll leave it for you to do this second part. And that's a good way, very effective way to compute the inverse, as long as you know that your matrix is diagonalizable. And you know these components of the diagonalization. And when I say components, I mean this pair of matrices, P and G. As a byproduct of this argument, actually, we can also see that my matrix is invertible. It's not always true, actually, the matrix is invertible. We all know that. Is invertible when the eigenvalue, because it will be invertible when G is invertible. But the inverse of G is the one where we invert each individual entry on a diagonal, and for that to be achievable, those entries, they must be non-zero. So here's a nice criterion for the invertibility of a matrix which is diagonalizable. Matrix is invertible if and only if every eigenvalue, n of them, are non-zero. And when the matrix is invertible, the last piece of this slide, which I'd like to mention, is you can also compute the negative powers of matrix A in a similar way. Look at this. If you want to compute the negative power, A to the negative k, all you have to do is this. You have to make the comment that A to the negative k is simply in one single inverse of A to the positive k. For this inverse of A, you do have a diagonalization formula. You can think of this identity, by the way, as a diagonalization representation for the inverse matrix, isn't it? Because you have diagonal matrices in the middle and P inverse on sides. So you can use this identity for the A inverse matrix. That's what I mean by the dots here. I'm hiding this presentation again. That will be like this if you just follow the same chain of manipulations. And that is the expression for the inverse. It's a very simple argument, as a matter of fact, but of course it rests on the really heavy machinery we built before, and it just opens lots of possibilities in matrix calculus. Huge amount of possibilities. You will see just very, very little fraction of those possibilities in this topic. Later on, those of you who will continue your math studies, you will see a lot more possibilities. Any questions, please?